Hello, shall we start?
Yeah, can we take the control, sir?
Yes, let me just okay. So this is plenary session 5. We'll be discussing scientific articles, presentations on enabling technologies for space exploration. The convener for this session is Professor Tirtha Pratim Das. The co-conveners are N. Raghumiti sir, M. Durga Rao sir, and V.K. Rana sir. The session chair for this session is Tirtha Pratim Das sir and M. Durga Rao sir. So we request the esteemed chairs, co-chairs, conveners, and co-conveners to take over the further proceeding of the session. Over to you, sir.
Yeah. Good afternoon to all. Welcome to NSSS 2022 plenary session 5, day 1 proceedings. Here I am Durga Rao from NARL. I am taking as chair due to unavoidable reasons of with Dr. TP Das. And today co-chair is Dr. Vikram Rana from RRI for the present session. So this session is basically on enabling the technologies for space exploration. In the morning session, we already heard from Chairman ISRO and Scientific Secretary. This session is having very good impact on ISRO future programs. That morning, we already listened from these two dignitaries. And in a brief, this session starts with the invited talk by Dr. K. Rajiv sir, Director SPL, followed by 4 flash presentations, which is having 2 minutes each duration, and 3 oral presentations, each of having 20 minutes durations. With this, I will invite our co-chair, Dr. V. Rana. If you have any points, you can add. Then after that, I will be introducing our invited lecture.
No, I think this is Vikram Rana from RRI. I will be acting as a co-chair. And I think as Professor Durga Rao mentioned, I think he has introduced the section, so I don't have anything to add. So I think we can go ahead with the session.
Yes, sir. Then actually, now I will be introducing today. First, we have first plenary session. This is will be developed by Dr. K. Rajiv sir. Now I'll briefly I will introduce Dr. K. Rajiv sir about to the community. So Dr. K. Rajiv sir, he obtained PhD in physics from University of Kerala and joined Space Physics Laboratory, Vikram Sarabhai Space Center in 1993. He was a postdoctoral research physicist at Scripps University Institute of Oceanography, University of California, San Diego, USA. Currently, he is the director of Space Physics Laboratory, SPL, VSSC Trivandrum, and he is the principal scientist of the National IGBP Nobel Project. He is the Indian representative to COSPAR Council and the member of the Research Advisory Committees of the Indian Institute of Geomagnetism, Mumbai, Indian Institute of Tropical Meteorology, IITM Pune, National Atmospheric Research Laboratory, NARL Tirupati, and his areas of research includes atmospheric aerosols, clouds, radiation, middle atmosphere dynamics, boundary layer physics, and satellite and LiDAR-based atmosphere remote sensing. He has developed state-of-the-art inversion technique for the deriving aerosol and cloud properties from the global passive satellite radiometer observations. He has published more than 70 research papers in peer-reviewed journals with very good impact factor in the international journals. 4 researchers obtained PhD under his esteemed guidance in the due course. And ISRO and NASA Earth Observatory released new items on his findings on aerosols, clouds, and radiative impact. He is playing a lead role in the planning and development of the scientific payloads for the space and planetary observations at SPL VSSC. With this brief introduction, I invite Dr. Rajiv sir to deliver his presentation on science experiments with PSLV stage 4 orbital platform. Sir, the stage is yours, sir, for next 45 minutes. At 35 minutes, I will give you a small indication to you, sir. Over to you, sir.
Yeah. Thank you, Dr. Durga Rao and Dr. Vikram Rana. Thank you for the kind introduction. And I am also thankful to the NSS organizers for giving me this opportunity to interact with you on the science experiments that we can do or we have been doing with the PS4 orbital platform. Actually, before starting this, I got a lot of help from Sri S.R. Biju. He is the project director of PSLV, and also from my colleagues at SPL, especially Tarun and Vineet. So now let us go to the lecture straight away. I'm going to share it, share the desktop, share the window. And are you able to see the window now? Are you able to see the presentation now?
Sir, PPT is not visible. Our window is visible.
Okay, okay. Just 1 minute. Unshare. Then share it. Screen, full desktop. Now can you see the window?
Yes, sir.
I mean,
yes.
the PPT?
Yes, sir. Yes, sir.
Okay. Thank you. So, okay. So my audio is clear? Hello?
Yes, sir. You are loud and clear, sir.
Okay. Okay. So we will go ahead with the presentation. Enabling technologies for space exploration, science experiments with the PSLV stage 4 that we call PS4 orbital platform. You know, PSLV is one of the main workhorses of ISRO with a very proven and incredible track record of success. For a first of its kind in any space agency in the world, a spent stage of a rocket was thought to be converted to a space laboratory by ISRO. This is the first of its kind by any space agency. And that is what actually 3 flights have already been completed with this. Each phase there were evolutions from the primitive thing to the advanced thing, and still there are scope for not only scope plans for the future expansion or future facilities getting added to that, depending on the user demand. User demand is the primary driver for the PS4 experimental platform. PSLV has 4 stages. I'm not going into the much detail, but then without knowing the structure, we will not be able to move further. So it has the core, and then you have the strap-ons. So you have the stage 1 and the strap-ons around it. You have the stage 2 above that, and stage 3 above that, and at the top you have the stage 4. That is what is given here. Okay, the stage 4, and which will be actually projecting the satellite to the desired orbit. The satellite is mounted on top of that, and it is covered with the heat shield. An expanded view is shown here. Now it is this stage, this PS4, what is indicated here. This is the one which will be orbiting. Usually what happens is it will go to space and then orbit, or maybe deorbited to back to the ocean or at a place. Instead, this is converted to a space laboratory with the extra fuel that is available with that. Okay. So the way it works is the PSLV has a sequence of operation, right from the launch pad, projecting it. You have the separation of the strap-ons, then the first stage separation, ignition of the second stage. Then you have the heat shield separation. This is an important sequence. I'll come to that. Why? Heat shield separation, and then the separation of PS2, ignition of PS3, separation of PS3, then ignition of PS4, cutoff of PS4, and then the satellite separation. This is a sequence. After the satellite separation, it has a provision for the satellite to be changed in its orbit, suitable for the payload of, the PS4 orbital platform. That is what is the last thing that will be done. And here, what is shown here, this is for the C45. That is the launch C45. This is what the time. The table shows the time and the local altitude. With respect to the local thing. So local altitude and the initial velocity attained. But you can see here is after PS4 is cut off, then the orbital, the satellite got separated at 6901 second. Subsequently, the RCS is started to change the orbit to the desired thing, and again orbital change took place. Actually, it is all experiments it has provision. That is one of the beauty of this thing. It has provision to change the orbit from the usual PSLV PS4 stage where you leave it. Instead of that, you can change the orbit, either change the altitude or change the orbital plane, depending on the amount of fuel availability. And then you can have the experiment, and there it will be orbiting continuously, and it will be a stable platform. Why I showed this sequence is also because usually the payloads that are kept in the PS4, that is in the orbital platform, will not be switched on usually till the satellite separation, because the safety of the satellite and the whole operation is of paramount importance. So usually that will not happen. But then in a scenario where they have the project has 100% confidence that this payload is not going to interfere with any of the systems, with independent channels of operations, then after heat shield separation, the instrument is now facing the environment. It can, in principle, have the observations taking place. But then this is not the real way it is to be done. The assured way is after the PS4 separation, after the satellite separation. But in principle, it is possible after the heat shield, because why this is important is because while the heat shield is separated, we can see that here the heat shield separation takes place at an altitude of around 100-115 kilometers. So, for example, you want to profile the ionosphere. It is important that we have to, have the profile from this region while the rocket is ascending. And one such experiment was done. I will come to that at the, when we are going to the science experiment phase. Okay, so these are the sequence of operations during the PSLV launch and the PS4 orbital platform converting to our PS4 orbital platform. As I told you, the PS4 orbital platform is the first of its kind to use a spent rocket stage as an orbital platform for science and technology experiments. It's the fourth stage of PSLV. It's a liquid stage. It is responsible for the precise injection of the payloads in the desired orbits. The advantage of liquid fuel, I don't have to tell to you that it can be cut off or switched on, at multiple times. It has the capability for orbit maneuver, which is very important for converting it to a science experiment, including restart and satellite injection in multiple orbits. It has two liquid engines and the RCS thrusters for propulsion and control. The overall length of the what is shown on the right, there are two figures that are shown. The one at the top is the PS4. You have the gas, the fuel cylinder and the exhaust. There is a deck that you can see here, that white ring-like thing. Actually, the instruments will be mounted on top of this deck. The PS4 instruments will be mounted on top of this deck. We will come to that in a short time. And above this, the satellite will be placed. So after the placement of this, it will be looking like this. Now it is connected to the PS3, the third stage, and this is the fourth stage. How to convert the spent stage to an orbital platform? It requires a lot of effort. Number one, you require power for an independent operation. So for that, you have to have solar panels. So the solar panels are actually, mounted on the, the gas, the chamber, not gas chamber, the liquid chamber. And on the surface, you can actually paste it with that. So it's a flexible solar panel. It is pasted on top of that with the, anchoring with the fore and end bracket and the aft end bracket. You have the onboard power generation from this with the flexible solar panel mounted around the tank. The charging of a 50 Ah lithium-ion battery using the power electronics. The spin stabilization is in preferred orientation is done to maximize the power generation. For C45, the power generation was 200 watt per watts, but then there is a small cyclic variation superposed on that. The power that could be generated, the voltage that could be delivered is 30 volt. Okay. So this is important for the payload subsequently for powering for its operation. The second main thing that is required is the capability to accept telecommand and give telemetry. The telecommand telemetry interface, we have the standard S-band telecommand interface with the provision to uplink the 25 commands up to. And the telemetry interface is again standard S-band telemetry interface. The telemetry data will be coming. The data, actually the data that the instrument is also going to give you is coming to the ground station through the telemetry. And it will be downlinking to the ISRO ground stations where the data will be received, deciphered, and it will be given to the user. And the telecommand, the importance is in addition to the operation in PS4, the telecommand also will give you, some of the payloads will require switch on, switch off, or some other modes of operation, which can be commanded from the ground through the telecommand interface. But in PS4, it will be limited because of the total duration of the experiment itself. So far, what was conducted, so it will not be a very, very large number of uplinks. It will be limited number of uplinks because of practical reason. But in future, if there are more demands, and as the based on the demand, there will be, of course, the capabilities also will increase. This also can be enhanced. The other interface that is essential is the stabilization of the platform. PS4 is a stable platform for microgravity experiments as well as for the space experiments. The orbit control is done with the RCS thrusters. It can store the data. That's also very important because it is not just the observations that are being done and then straight away the observations are taken and then telemetred. There is provision to do that. There's also provision to store the data up to 1 GB. And it can be retransmitted when the PS4 is coming in the vicinity of the ground station. Okay. And, as an indication for the mechanical interface, what is the maximum size that is possible for the payload? It is flexible. It can be 1U, 2U, 3U, 6U, or 12U. Actually, 1U is around 10 centimeter, 10 centimeter, 10 centimeter. Okay, that's the dimension. So it can be up to 12U. But again, it will not be very strict. It is not that exactly 10.00. There is a little bit adjustment is required, but then this is a kind of expectations as far as the mechanical interface is concerned for the scientific payloads. So far, the PS4 orbital missions have completed 3 such missions, starting from C38, C44, and C45. And C38 was the very first one. Where the first science experiment also was done, and incidentally it was from SPL. The LP and NV payloads were flown on board that, and then good results were produced, which was published in the literature. It is available for you to refer to. And C44, again, there were no scientific payloads per se, but then there were certain other technology payloads and maneuvering and all those things. And C45 had the scientific payload. The IAST's RPA, returning potential analyzer, as well as some other payloads from, one was from SAC and another was from the ham radio thing. We'll come to that in a short time. So the orbital platform features in a summary for people to work with is it provides power, it provides attitude control, it provides communication, and it has storage facility. All what you expect from a satellite is provided here. And this shows an example of in C45, the payloads and the other things mounted. This is what is shown here. Okay, so I told you there's a duck, the deck that we were projecting, showing earlier, and it will be mounted on top of the deck. So you cannot have very large, huge dimensions because the availability of the deck space is the one which is the limiting factor here. You cannot have much more than that, right? The main advantage of orbital platform, why orbital platform should be encouraged is because either commercially, off-the-shelf components that we call the commercial components, or the mill grade can be used in this kind of thing. Usually what is done is space grade, which is very costly, and several times you may not be even able to afford to have even one more component other than what is really intended for. This is what usually you face with when you are talking about the space grade components because they are extremely costly. Whereas The commercial off-shelf hardware is much cheaper than that, or the mill grade at the most. This is the type of components that you can use in Orbital platform. And the only thing is it has to be tested for the specified environmental conditions. There are certain environmental conditions that are, for example, hot soak, cold soak, thermal cycling, thermo vacuum, shock, vibration, all those things it has to undergo, because this, the spacecraft is going to face all that. So obviously all those things it has to undergo. But the commercial off-shelf items will, it is proven that it will satisfy all those things. The second thing, the main thing is actually radiation hardening is not required here, because radiation hardening is not something which is done here. All right, because that makes the space grade components much more costlier. The additional structural elements and adapters are also required to support the payload. Okay, and at these things, the last item, there will be strong, talks between the project and the user community, because the user community should be knowing what are all the things which are possible that will be able to interface with this. In PS4 C45 as an example, the payload, one of the payload was the advanced retarding potential analyzer for ionospheric studies to measure the ion and electron energy distribution in the ionosphere. It consists of 2 independent sensors to simultaneously measure electron as well as ion flux. The total mass was 3 kg and it consumed a power of 10 watt. The footprint was close to, this is a 2U kind of system, 200 by 200 by around 120 mm. Okay, so the measurements were compared with what is already available, published data, and it was shown to be in very good agreement. This is the one scientific payload that was flown on C45. I understand that the results are consolidated and the publication will be coming out soon. The second was on AMSAT India and URSC. This is actually an automatic packet reporting system, digipeater. It is not a science payload. It is a transmitter, a digipeater rather, for the AMSAT. It was extremely useful for the amateur radio satellite. And the most important thing is, even after 2 years, there was a letter from AMSAT to the project director, which he shared with me. Even after 2 years, the AMSAT is still working in onboard PS4. Okay. But only thing is now it is not in a controlled mode, because we will not be able to control the PS4 for a long time because of the limited availability of the fuel. But the system, the ARPS is still working. Still in the sense till 2 years. I mean for 2 years or more than that it was working. This is sort of a 1U type of system which used 12 watt power. 4 kilograms weight, and the RF output was 1 watt, and it used a frequency of 145.825. This is in the VHF domain, which is actually the permitted frequency for this. Another payload that was flown on PS4 is the automatic information system, where it receives the message transmitted globally from ships and store them in the internal memory and transfer to the ground stations during the visibility in the S-band. As far as science is concerned, it is only the RPA payload that was flown on C45. So the experimental potential experiments that can be done with the PS4 orbiting platform is first is undoubtedly microgravity, because microgravity, it offers a platform for microgravity experiments which is unique. The second is material science, because material science, in gravity or close to microgravity, the potential of PS4 in doing material science experiments is tremendous. Technology demonstration experiments, because there are certain payloads which can be flown, but then it has to be first tested, okay, in space. Usually, it may be risky if you are going to take that payload to space. So certain technology demonstration experiments can be carried out, because you can do it with the COTS kind of, the components. Student payloads, then it deorbit and re-entry for debris management. Earth atmospheric and space science experiments can be carried out. Tethered robot experiments. humanoid-based robotic experiments, biological experiments, and sample returns. So far, on the right side, the tethered robot or humanoid or biological or sample return experiments are not carried out, but based on the user community's requirement. In principle, it can be done because the capability exists. It's only the question of the fuel that is to be carried extra and the features to be added, but the capabilities exist. So in principle, PS4 orbiting platform is an ideal platform, first of its kind, which can be used for science experiments. Now let us go to some of the science experiments and the results that were obtained from PS4 so far, and also some of the experiments that are being planned for the future. First and foremost was the very first PS4 platform, IDEA payload, that is actually ionization density and electric field analyzer payload of Space Physics Laboratory, VSSC. It is the first space science measurements onboard PS4 platform. It was flown on C-38 and it was made in a very short time. And PS4, this has a heritage of flying in rockets. The rocket experiments for Surya Grahan experiment as well as the Saurex experiment. And it was mainly using codes kind of thing, except for one or two components which are mill-grade. Okay. The basic purpose was to monitor electron density, irregularity strength, and electric field during the polar orbits at 350 km and investigate the ionospheric processes, including the evolution of equatorial ionization anomaly, ESF, depending on the available data. This was the main objective. And it was also to measure the electron density and electric field at the top side of the ionosphere while the payload traverses from around 700 km to the PS4 orbiting altitude of 350 km. This was the intended thing. And the paper is published, Manju et al. In JSTP. The IDEA payload, it contained two sensors. One is the electron density and neutral wind to measure the sound electric field and electron density, and the Langmuir probe to measure electron density and irregularities. The Langmuir probe, it has the potential, you apply constant potential or you can have a varying potential. In this case, what was done is a fixed potential of 4 volt is applied to the spherical probe, which is insulated from the rocket body. And the current collected by the probe depends on the ambient electron density. The ionospheric irregularity strength can be determined from the fluctuations in electron densities once you have the continuous observations. And the payload electronics has been tested, developed and tested using CORDS component. And the package qualification, why I am stressing here is so that people will be having an idea about what is the kind of environmental tests or the other qualification tests required for their payloads to go. Initial standard room temperature, conditions tests. This means actually what are the intended, you power on, and then you can make whatever intended possible measurements. Certain measurements cannot be made because it require vacuum or it require electron density measurements. Such things will not be possible. But then you can have the electronics tested fully here. You have a 96-hour active burn-in test. Then comes the real tests that are required for the spaceborne system, that is vibration test. For each thing, the project will prescribe what is the vibration test that is required. In this case, it was random 7.8 G in all 3 axes for 1 minute. This will be prescribed by the project because it depends on, it can vary from mission to mission. Usually it will not vary much because PSLV, if it is a similar kind of system that is being used. And the vacuum test, it has to undergo a thermo vacuum test. It will be undergoing up to around 10⁻⁻⁶ torr for around 10 minutes with the package switched on. There will be a hot test where the temperature will be maintained at say 50 degrees centigrade or 60 degrees centigrade for a duration, say 5 hours, with the packet on for the last few hours. And the cold test, where the temperature will be brought down to a very low value of the order of say 10 degrees centigrade or around that. And again, the package will be on towards the end of it. And also there will be an acceleration test that is 3G, the 33G that was done here. Once it, once the payload is able to survive all these things, you can be confident that the payload will indeed work in space because there is, strong vibration as the payload is, the satellite, the PSLV is, lifting up. And also there will be very strong shocks that will be coming when stages are getting separated. So that is why all these tests are required, and also to see the survivability in the hostile conditions, if at all it goes into that kind of a domain. And the final SRC will be done, where it will be further tested that the payload is indeed working. The NV probe, actually the theoretical calculation shows that at around 1000 cc of electrodensity, it will be producing a a current of around 207 picoampere. And when it is of the order of 10 power 6, it will be around 360 nanoampere. So this is the kind of current level that NV is measuring. And similar is the case with Langmuir probe also. For around 1000, it will be 271 nanoampere. And for around 10 power 6 per cc of electron density, it will be measuring around 417 microampere, which need to be amplified. You can see that they are handling picoampere to nanoampere level of current, which need to be amplified and then detected. Recorded. The mass of NV is 1 kg, and while the mass of Langmuir probe is around 250 grams, it is very less. But of course, then comes the electronics. Total will be close to around 1 kg kind of thing for LP. The main result that has come out from this is, what you are seeing on the left side is the electron density that was measured by IDEA on 23rd June 2017. This is the C38 mission, and the red line shows that. And when you compare it with the cosmic observations for June 27 for the nearby closest location, right? All the features are well reproduced. Of course, there will be the variabilities are in the expected lines. What is more important is you are able to see a ledge towards the top, around above 500 kilometers, which is not seen in the cosmic data. So it can be an ionospheric ledge because, for example, people can talk about the upper ionospheric ledges or F3 layers and things like that. What they did is they also did the theoretical simulations and then found that actually it is limited to a very shorter geographical latitude and very short altitude range. Incidentally, finally, after the whole analysis is done, they found a very interesting observations. That is, before going to that, I would like to show you that the profiles here is available right from around, around 170 kilometer upwards, because the measurements were done after the heat shield was separated. Usually, as I told you in the beginning, PS4 orbital platform experiments usually will be done after the satellite separation. But in case, the payload, the project has the confidence, or you are able to convince the project without taking absolutely any risk, the payload operation, it will not hamper any of the things, then it is in principle possible. But then let me repeat it, the priority is for operations only after the satellite separations and coming to PS4 orbit. All right. The most interesting thing here is the observations. The ledge that was found is actually coming from the PS4 stage ignition itself. The first of its kind in-situ observations, the topside electron density enhancement concurrent with the operation of PS4 stage demonstrates the plausible role of rocket burn and exhaust gases in modulating the ionosphere in its vicinity. This is one of the primary observations from the group, in addition to the profile that we have already seen here. Actually, it was not a true ledge that we say in the ionospheric thing, but rather it is an effect of the PS4 itself. And that shows how this the rocket launch can have an influence, or the rocket burn can have an influence in modulating the ionosphere in its vicinity. I took these lines from their conclusion statement, so I did not modify anything. This is as per the authors. Now let us come to some of the experiments that are proposed. There are several experiments. There was an announcement of opportunity for the experiments on board PS4. I believe that there were several things that were submitted. But what I am going to present here is only those things for which I am directly aware of the thing. And also there also I did not pick up all, but then I picked up a couple of things which will be truly representative of the variety of things. I'm not going into the very exhaustive details of what are all the things presented, and some of them should not be also, because they are all in the planning phase by different scientific communities, so I cannot present it here. But still, for your kind information, there is an announcement of opportunity for the user community to use PS4 on a variety of science experiments. It can be space science, it can be biological experiments, it can be microgravity, material science, and so on and so forth. So one of the proposed payloads for the upcoming mission is the atomic oxygen sensor. Why atomic oxygen sensor is because, the atomic oxygen is the most abundant atmospheric species in the altitude range above around 500 to approximately around 500 kilometers. Produced by the photo dissociation of molecular oxygen in the EUV range, especially less than 243 nanometer. It has a strong solar cycle dependence, and limited measurements of atomic oxygen profiles only are available. Mostly they are available through the models. What is shown on the right side is the altitude profiles, it's modeled profiles of various components, and where the oxygen, atomic oxygen, is shown in green line. That you can see that, that is increasing from around 100 and then shows a monotonic decrease. But then it is overall, it is one of the most dominant species, at least up to around 500 kilometers. Of course, this profile may have a little bit variability depending on the kind of, the model that you use. But overall, it is one of the most dominant components in the up to around 500 kilometers. And what is most important is actually it is highly reactive and cause adverse effects such as material degradation. It's important. It has a lot of applications, in the satellite design material itself, because of the reactive nature and the adverse effects that it can produce. And it has received considerable attention in the space science and engineering community. The scientific objective of the atomic oxygen sensor, this is proposed by Vineet et al. From Space Physics Laboratory, is to study the spatiotemporal variations of atomic oxygen in the thermosphere and its influence in the ionospheric processes and photochemistry of the region, and to study the altitude variation of atomic oxygen during the launch, since it's an important as far as the plasma density and energetics of the mesosphere and thermosphere region is concerned. Basically the sensor proposed is a metal semiconductor metal oxide sensor, zinc oxide here, because the chemisorption of the species onto the surface of a semiconductor changes its electrical conductivity. So the degradation that is going to take place will deplete the layer and its conductivity. And once you have a thin film of semiconductor, the induced surface changes will be dominated by the surface properties itself, and then the surface conductivity, which is actually controlled by the atomic oxygen present there. The metal oxide semiconductors have large band gaps and low number density of intrinsic charge carriers, which is one of its advantage. One of the main benefits of the semiconductor sensors is that it is reusable. It can regenerate their pre-exposure properties after heating, allowing the sensors to be reused many times. This is an experiment. This is an example of the laboratory measurements that were carried out. The line, the thin line shows the atomic oxygen source on in the laboratory, whereas the circle and then the cross and the line joining them shows the resistance, the temperature. I beg your pardon. The resistance is shown in the thin line, and the temperature is shown as the crosses that will be coming in. So when you are switching on the, with the temperature, of course, you have the resistance changes. And the moment your atomic oxygen sensor, atomic oxygen source is on, there is a significant reduction, change in the resistance. And this is the property that is going to be used. The change in resistance associated with the atomic oxygen exposure is the one which can be used to quantify it. Essentially, what you have to measure is the conductivity. So what they are going to have is the sensor layout is shown here. One will be zinc oxide film here, and then an equivalent film, but it will be coated over that with the silicon dioxide coating. The idea here is the red one is exposed to the environment. So there will be atomic oxygen, will be reacting with it, whereas the yellow one will not be affected by that. Except for that, these two sensors are the same, so you'll be able to isolate the effect of the atomic oxygen. There are 4 sensors, each of say 1 millimeter by 0.5 millimeter size. each in alumina substrate. And the back of the substrate, they provide a ruthenium oxide heater element. All right. So the electronic circuit contains a circuitry for 2-point film resistance measurement. It's a rather, a simple approach for doing this. And the maximum power consumption is about 5 watts, and the total mass is going to be around 1.5 kg. The system has been designed and it is now undergoing fabrication and subsequently to the lab test. The maximum data storage that is expected here is of the order of 10 MB per orbit. The total size is going to be something like 1U or slightly more than that. And the power requirement, as we have already told, it is of the order of 5 watts. Okay. The next experiment that is planned here is the electron temperature analyzer, ETA. This is to measure the ionospheric electron temperature and electron density. To study the Kittoer ionization anomaly and associated TE variations and TE enhancements due to the high latitude energy input to the ionosphere. Incidentally, why I selected this particular thing is because of the following. A similar payload has been selected for the upcoming Aeronomy satellite mission, Disha L and Disha H, and for Venus mission. And this gives us an opportunity to test it in PS4, where it is really facing the space environment. And then, we will be able to derive better output when we are really, flying in a satellite mission. So this is another thing where you have an idea, you want to, experiment it with, and then it can be applied to a satellite rather than, straight away going to a satellite. Something like proof of concept to the output. This is one of the most interesting aspects of that. Basically, this sensor is a circular electrode, tin coated, and divided into 2 semicircles, and it is the electrode is used for charge collection, and the other semicircle will be used as a reference electrode. Sorry, Smita, pardon me.
35 minutes.
Okay. I'll be finishing in time. No problem. So basically, the way it is going to work is sinusoidal voltage is going to be applied with varying voltage levels, and the floating potential will be measured. That is to estimate TE, that is the electron temperature. The second is the frequency will be swept from around 200 kilohertz to 1 megahertz, but then the amplitude of the thing will be kept as 0.5 volt to obtain the floating potential shift with the frequency, that is to derive the number concentration of electron density. And the total mass is going to be something like 0.5 kg, and mass for the sensor, for the boom, it is 1 kg, and electronics is going to be another 1 kg. So total around 2.5 kg, and power will be around 5 watt. And the total volume that it is going to occupy is, a 12 centimeter dia, a flat disk. All right. Sorry, just 1 minute. Right. Another very interesting concept that Rajkumar Choudhury and others have brought in, again from SPL, AVN and IASU combined effort, is to measure the plasmaspheric electron density by flowing, a NAVIC receiver in the PS4. When you have a receiver, NAVIC kind of receiver at the ground or GPS receiver at the ground, you are able to measure how much is the, total electron content. Now, if it is flown on board a PS4, what it is going to give is the plasmaspheric electron density above the satellite altitude, which is not much measured. There are only very little measurements of the plasmaspheric electron density because of, for example, ionosonde doesn't, go above the thing, and otherwise incoherent scatter measurements. So the observations are only very limited. So the basic concept is same as what you are going to do, what you are doing in the ground. But the challenge here is to have a NAVIC receiver in the PS4 and to measure with sufficient accuracy to measure the plasmaspheric electron density. The other set of experiments, as I told you, there are several TDP experiments, for example, solar occultation or multi-angle polarization. There are several such things which can be planned here, because one more advantage of PS4 upcoming, another development that is taking place parallelly is a robotic arm, which can be moved in multiple planes. So including, you can have the deployment and one thing. So it's a robotic arm. So such things also can be used here. For example, in solar occultation, you have to track the sun, the same dot in the sun. Or the multi-angle polarization, you need to have multiple angles of observation before flying into the satellite with all these kind of costly sensors and things like that. You will be able to confirm that your concept or your sensor or your payload will be able to deliver the goods here. For such experiments where it doesn't have a history or it doesn't have a precedence earlier. One thing which I was thinking about, which is very useful for PS4, is the monitoring of the energetic charged particle intrusion over the South Atlantic anomaly. All right, the South Atlantic anomaly extending from the South American region to the South African region to the Atlantic, through the Atlantic, it produces a dent in the Earth's magnetic field, and you have large number of charged particles coming from the radiation belts. All right, so in these regions, actually, the flux of energetic particles is higher, which is expected. They are going to have several effects on the electronics itself. The payload electronics itself can be affected by that, because you have the single electron upset or single event upset or latch up. So such things is more probable over such regions. So one of the thing is, PS4 platform can be used to monitor this also, because in the multiple orbits it is going to pass through this. Only thing is, you need to have measurement of the fluxes of charged particles for different energy ranges or the in the platform, and the atmospheric characteristics correspondingly, and the impact of charged particles can be assessed. It has application in assessment of the energetic charged particles on spacecraft electronics also, in addition to the science which we are going to do. The map shows the South Atlantic anomaly. The strength of the magnetic field, which is measured by ESA's SWAM satellites, published already. Of course, I have finished my space science experiments, but what is most important is there is an equal or more important thing in microgravity environments. Without having a mention of that, it will not be complete. The microgravity will influence substances in the liquid and gaseous phases. Especially, it will alter, crystal growth, for example, to fluid mixing, to separation of the gases and liquids, heat transfer, solidification, combustion, host of processes it is going to affect it. Generation of microgravity in Earth is possible only for a very short duration. You have the, drop experiments, or the parabolic flights, and the other laboratory things. But then they are all for very short duration, probably of the order of few seconds to maybe few tens of seconds, maybe of the order of a few minutes, not more than that. Whereas PS4 offers you much more thing. But in the current thing, you will be able to do the experiment there, but then you should be able to monitor also what are the features that will be coming, and then transfer the data. The things that will be useful, important here is the material science, behavior of fluids. In pharmaceuticals, for example, drug development, this is a phenomenal application. I was going through the literature. I found that there is something which is, sent into space and then recovered back. It's called a photon, capsules, which can be recovered back. Actually, it is being used, it's called a space pharma in industry, called space pharma for drug development. So it's very similar is the case with PS4 kind of thing. So it's a unique environment for orbiting platform, enables the research in many fields that benefit humanity as a whole in both short and long term. And benefits can be to R&D in drug discovery, nanotechnology, material science, tissue engineering, agriculture. Of course, the list is never ending. And this is an example of how microgravity will be affecting. I will not go into the details of such things. What is more important here is, as I told you, PS4 can be, its features can be expanded. For example, the longer duration of the stabilization of the platform, re-entry, deorbiting and re-entry. All those things are possible, but then it will be based on user demand. Okay, because capability is already demonstrated. Multiple orbits, deorbiting to another orbit, changing the orbital plane. All those things are already demonstrated. further capability addition is possible, but then it is only with the Orbital platform, with the user demand. All right. So with this, I thank you for your kindly listening to me, and I'm very much thankful to Dr. Biju, Project Director, PSLV, Dr. Tarun Pant, Head of ITMP and VSSC, SPL, and Dr. Vineet, who has, these people helped me in making the presentations very much. Thank you very much.
Thank you very much for your enlightening, sir, showing all the possibilities of PS4 platform for the future experiments. And here in the chat box, we have received a few questions from K. Ramesh, sir. I will just read out that. He want to curiously know, are these experiments are substitute any data gaps provided by the other experiments, like satellite experiments, for providing continuous data? That is one question, sir.
Yeah, this is an interesting question. Actually, as I told you, there are certain, for example, in situ measurements of the ionospheric thing, which can be done only with either orbital platform or, of course, a satellite in that particular orbit. But then a satellite cannot be used for profiling, or it cannot be simply changed into multiple orbits in a short duration, because satellites are not intended for such purposes. So that way it is very unique. The experiment, for example, what was done in LP. LP is a very simple experiment. LP is not a very, very complicated experiment. It's a rather simple experiment. But then the science potential of that is because of the PS4 platform, where you are able to profile it, and also you are able to have it with multiple orbits. Of course, it was only made for 10 orbit, because I told you that was an evolution phase, right in the C38. So it was made only for 10 orbits. Subsequently, the platform was not, stabilized for science experiments, and then the data transmission and things like that. But then when you have an enduring thing, that kind of thing cannot be repeated with satellite, conventional satellite kind of thing. So definitely the kind of data that was generated from at least some of them are unique in that manner. The second thing is, as I told you in the beginning, to make a satellite a payload in a satellite require very, very costly equipment, components, space grid components. If you have a concept which is to be proven, this offers an ideal platform, so that you will be able to do the experiment with that, and then prove that it will be indeed able to work. And sometimes you may not be even knowing the inversion technique that is to be developed. You may be doing the overall thing, but then when you are really working with the data only, you will know this inversion will not work. So you require another configuration of the observations, like, for example, multi-angle polarization image, or optimization of the angles or polarization. All those kind of things can be done with such experiments, such payloads. That is the power of this.
Very nice, sir. Thank you very much for your patience teaching, because this concept is new for most of the people, those who are really watching this conference. Thank you. We thank you very much from LOC side also, sir. Thank you very much, sir.
Thank you very much, and thank you for the organizers also for giving me this opportunity to interact with you. Thank you very much.
This is to LOC.
Yes, sir. Please.
Yeah, we'll be taking up next flash presentations.
Okay.
Yeah, first presentation from Pragnesh Dev. If he's available, he can load his presentation. This is for 2 minutes. Pragnesh, are you available?
Yeah, he is available. I'm just giving him the contract.
Yeah.
Pragnesh is already presented. He can go ahead.
Looks like he's muted.
Hello. Hello. Hello.
Yes, sir. Your voice is audible.
I'm available. I'm sharing my screen now.
You share your presentation, sir.
Okay, okay.
All the flash presenters, get ready with your presentation slide so that it will be fast. There won't be any.
My poster is presented now?
Yeah, you can make it. Yes, sir. Other screen. It was visible previously.
Okay, okay, sir. So I am just pressing my idea. What is there in the poster? What we are doing? All right, sir. Can I present my idea?
No, now it is not visible.
Okay, wait a minute. Give me time. All right, I'm presenting now. Oh, already I have saved now, sir.
Yeah, now it is visible.
Visible, okay, fine.
So now you closed it. You have closed it. Previously
okay,
it was.
okay, I understand now. No, give me. Okay, I'll do it one second. Yeah. I hope now it is visible now. Now is it visible, sir?
Not yet, sir.
Just seeing your team screen.
Huh?
We are just seeing your Teams app screen.
Team app screen from screen awakening.
Yes.
All right. Now, is it possible now to see the screen now, sir?
Now we can see your screen, so you can just try to open your poster, minimize the Microsoft Teams and open your poster. Yeah, it's visible.
My poster is open now. Can I go ahead now, sir? Can I go ahead, sir?
Can you make it full screen? Just go to the presentation mode. Can you just make this presentation mode? Just
presentation mode, but
F5.
F5, okay. This is F5.
It's like he's disconnected right now. So can we move on to the next speaker and then come back to him later?
Hello?
Yes, we can hear you. We cannot see your screen.
Already now I have said I hope for this video now. Now is it
We are seeing your browser. We are not seeing your browser now.
But what can I do, sir? Stop sharing already. This is showing screen has played.
You just minimize the Microsoft Teams and just go to the presentation. Yeah, this slide. Now in the right bottom, now we can see.
Okay, now is it okay, sir?
Yeah. Just
okay. So I'm present. I should present now.
Yeah, sure.
Okay, sir. So my presentation would be my title of presentation is nickel zinc Fe2O4. This is a potential catalyst for thermal decomposition of ammonium perchlorate and the burn rate modifier for APHTPB based proposal. So this is my title. Now I will give you the brief idea what we have done in this work. So we are utilizing methyl nitrate salt and sodium hydroxide as a precipitate agent. By which we have synthesized nickel zinc ferrite NiZnF particles were successfully synthesized using a route called co-precipitation method. And the effect of 1% nickel ZnF additives on the thermal decomposition of AP and the burn rate of AT-based composite solid propellant was investigated. The 5 isoconversion methods are utilized to determine the activation energy of the ammonium perchlorate in the presence of catalyst using DSC, just the differences coming in the calorimetry data, and the acquisition device study of AT and propellant with and without nickel zinc ferrite catalyst was carried out using a cube furnace. Our DSC results shows suggest that the NiZNF is showing a good catalytic activity on the thermal decomposition of ammonium perchlorate, and which is decreasing the thermal decomposition temperature from 90.68 degrees and the activation energy to a great degree. Now, in this case, the transition metal we have utilized for our purpose, and by using a transition metal, the detailed synthesis has been given. So already this is the co-detailed precipitation groups are given, and the KGA and DSC data we have summarized. So as far as the result part is concerned, apart from that, we have already done the AFM analysis, and through this AFM analysis, we have calculated the size, particle size of the technique, and the various other techniques like BET, BET technique we used for the surface analysis measurement that study we have done, or DSC thermogram we have performed in the presence of non-additive and in presence of additive. So the results are summarized in these two tables. So if you look at to this result presented over here, this nickel zinc ferrite that gives a HTV peak at 1%, which is 304.32, whereas the pure is giving 395. So it clearly shows that
10 seconds.
Sorry?
10 seconds are there.
Okay. So this is the catalytic activity, and if you look at the series of data that suggests that catalyst is capable enough to reduce the temperature and subsequently reduce the activation energy, and it proves the catalytic activity of nickel zinc ferrite. So this is all from my presentation side.
Thank you, sir.
Thank you.
You can stop sharing your thing so that.
Okay, fine, sir. Thank you.
The next presenter. From
yes, sir.
Study.
Yes, sir.
Simulation studies of NMPCC for nonlinear model of Hexoon EDU 450 quadrotor.
Sir, is the screen visible?
Not yet. Yeah, now it's visible. You can make a full presentation.
Okay, sir.
Your time starts now.
Okay, sir. The title of my today's seminar is Simulation Studies of NMPC for a Non-Linear Model of Hexoon EDU 450 quadrotor. So first is the introduction. Nowadays, the quadrotors have been used widely in various areas such as surveillance, transportation, agriculture, inspection, and maintenance of the last access and the power lines. So whenever we go for this kinds of applications, the trajectory tracking control is one of the most critical problem. So in order to obtain a proper trajectory tracking, NMPC is being developed. So figure 1 shows the prototype of Hexoon EDU 450 quadrotor. Next is the system dynamics. So here we have considered the 12 states, that is XYZ, VX, VY, VZ, phi theta xi, and PQR, and 4 inputs U1, U2, U2, U4, and the output and 3 outputs, that is XYZ. So these are the 12 ordinary first order differential equations. Next is the parameter identification using the first principal model. So these are the images that were captured while weighing the quadrotor and its corresponding parts. So next is the calculation of the moment of inertia. So in order to calculate the moment of inertia, the inertia of individual components are calculated. First is the inertia of the box, then inertia of the leg horizon, motors, and landing gears and the propeller. So then the rotor inertia. So moment of inertia about XYZ is nothing but the addition of all the inertia of all the components. So next is the this table shows the parameters that have been estimated, that is mass, that is 1.343 kg, length of the arm 0.225 kg, IX IZ is the moment of inertia, JR is the rotor moment of inertia, CD is the drag coefficient, CT is the thrust coefficient, G is the acceleration due to gravity. Next is the nonlinear model predictive controller. So this mainly uses the current state in order to solve the optimization problem, which is defined with a certain objective function in order to control the control action and the desired input and the state constants. So objective function that has been defined is nothing but the difference square root of difference between the actual state and the desired state, and these are the sum of the constants. So these two images shows the simulation results that are obtained by considering the rectangular trajectory. So conclusion from the experiment is the result shows the accurate tracking for the trajectory given, and the future work can be carried out by implementing the developed algorithm into the real-time quad rotor. So these are the some of the references. Thank you.
Thank you, sir. Next one, Martian rover for extraterrestrial research by Andreas Day, SRMIST, Katak, Lucknow. You can load your presentation.
Hello.
Yeah.
Yeah, wait, I'll present my screen.
You can load your presentation.
Is it visible?
Yeah, it's visible. You can go ahead. 2 minutes for you. Time starts now.
Good afternoon. My name is Antariksh Ray, and today I'm here to present on the topic Martian rover for extraterrestrial research. So first thing, as we all know, that there is a lot of research going on extraterrestrial life in Mars, especially in the Martian lava tubes. So our focus of the rover is to excavate this region of Martian lava tubes. Our mechanical design consists of a 6-legged hexapod mechanism, which can switch into a 4-wheel drive whenever required. This 6-wheeled hexapod is able to traverse using spider motion, whereas the wheel drive is like a normal rover. We also have 2 hybrid limbs. One is a gripper and another one is an auger to collect samples from the surface of Martian lava tubes. Other than this, we have a launching mechanism. This collects sealing samples inside the lava tubes so that we can capture stalactites and stalagmites. Our science payload consists of sensors that can measure temperature, humidity, pH, and acidity. This generally measures the regoliths, which is the soil, the colloids, which provide us visual biosignatures, and the crystals and stalactites, stalagmites formations inside the lava tubes. So the gas sensors provide us data about the gases such as carbon dioxide, carbon monoxide, N2O, N2, which tell us about the presence of biosignatures. The rover is also equipped with EDX spectrometer and an organic camera to detect biomolecules and presence of other compounds. These all biosignatures will help us to determine the presence of extinct or extant life on Mars. Our autonomous subsystem consists of a 3D mapping lidar that maps the surrounding, and using SLAM technology, it is able. Yeah, so we hope that someday we are able to discover the mysteries of Mars. Thank you.
Thank you very much. The next presentation is on fortifying the development of Mars colonization and space biology research in India by Ella Verson, Space Development Nexus. Sir, you can load your presentation.
Hear me?
We can hear you. You can share your presentation.
Can you hear me?
Yeah, your voice is loud and clear. You can share your PPT.
Yeah, just a minute.
You can
Screen
make,
visible?
yeah, screen is visible. You can,
Yeah.
your time starts.
I have 4 minutes, right?
2 minutes.
Okay. So good afternoon, everyone. This is Ilankurili Ilavarisal. So we are going to present on fortifying the development of Mars colonization and space biology research in India, basically empowering interplanetary life education. So we understand the importance of going and settling on different planetary bodies in the coming decades. So many programs have been stacked upon in the field of space sciences and exploration so far. But the bridge between getting to other planetary bodies is the knowledge, which is very important. And it's been happening around the world for quite a amount of time in the field of space education. But what we're going to we are going to do in India in the meantime is what we are going to discuss about. So basically, it all starts from a combination of education plus field exposure. So that is where astrobiology studies and Mars settlement and exploration education comes into picture, where the importance of studying about Mars, various topics like plasma physics, terraforming, architecture on Mars, life support systems, and health, human health in space, etc., will be dealt. So it's been currently done by a few of the pioneers in India. So these are some of the co-authors of this project. And this is now being done in with a collaboration with a university called the Mars University, which is an international academic research organization based at the US. So these are the founding members of Mars University, who are also the pioneers of Mars research. And their mission and vision is to encourage students to enhance the multidisciplinary approach to not just to get to planets or to technologically design space exploration systems, but also to understand holistically how everything would work out in the future in a more a rational way. So it's been done in India by Amity University, Mumbai, by establishing the Amity Research Station at
10 seconds more.
Yeah. And this is a prototype which we might see on Mars in the future, and this is developed currently by India. So with the collaboration of Mars University, the APEC program, that is Asia Pacific program, is going to be established in India. So if you are a person interested in Mars research and willing to learn more, so this would be a one-stop. So this is our project and our vision. Thank you so much for listening to me.
Thank you so much. So with these flash presentations are completed, 4 numbers. Now we'll be taking up our oral presentations. First one we'll be having on sounding rockets, space science research with sounding rockets. Binay Joseph from BSSC. Sir, kindly share your presentation. You can start, sir. Sir, your mic is muted, sir. Your mic is muted, sir. Sir, you can unmute and start. Sir, your voice is not clear. We are not hearing your voice. Maybe unmute you. Not, sir, not audible.
Can organizer unmute?
Actually, sir is actually unmuted, and we can see his speaker on, but we cannot hear his sound. As we received an information earlier, Vinay sir has joined as HRDT trainings. From this account, Dr. Vinay Joseph, Virender sir, and Srilatha ji, they'll be presenting their presentations from this account. And this particular account has presenter rights, so they will be able to unmute themselves and show their presentation at any point of time they are ready.
Okay.
Am I audible now?
Yes, sir.
Okay.
Yes, sir. You can share your presentation, sir.
Yeah. Is my presentation visible?
Yes, sir.
Okay,
yes, sir.
Thank you. Good evening. I'm Binoy Joseph, Project Director of the Advanced Technology Vehicles and Sounding Rockets program, along with my colleague and co-author, Mr. Alex John. About to give you an overview of the space science research you can do using sounding rockets. As you know, sounding rockets can be used as a platform for your experiments, science experiments with microgravity and upper atmospheric studies, and also flight testing of new avionics. The advantage is that the launch will be near the Earth's magnetic equator. The story of sounding rockets goes along with the story of ISRO, as laid down by our visionary founder or the father of the space program, Dr. Vikram Sarabhai. He established in 1963 the Tumba Equatorial Rocket Launching Station, which has the advantage of being very close to the geomagnetic equator and an ideal launch site for meteorological and upper atmospheric research. The first sounding rocket was launched from Thales on November 21st, 1963 as a Nike Apache sounding rocket from the United States. Parallelly, the indigenization of sounding rockets development was also taken up and was successfully launched in November 20, 1967 with the launch of a very small sounding rocket, the RH-75. Further, the Thales facility was dedicated to the United Nations in 1968, and after that, we have launched 3,542 launches so far of our various vehicles which have developed on the way. The RH-200, the 300, the 560 ATV, and so on, including rockets from other nations, more than 1,300 launches we had from other nations. We also have regular RH-200 monthly launches for meteorological purposes. Now, let me tell you what is a sounding rocket. It's a small research rocket that can carry scientific payloads on board to take science in situ measurements and perform experiments during its suborbital flights. The payload forms, as you see in this figure here, the payload forms the upper portion, and then there's a motor, can be either a single stage or two-stage rocket, which will take the payload to some desired altitude and also give you the data and telemetry. The avionics also includes the instrumentation and sequencing system, which are also required for the data. Now, basically to note that sounding rockets do not intend to place a payload into orbit, but they go to an altitude and come back. All along these 50 odd years, we have had so many rockets which have been developed, and right now we have the operational RH-200, the 300 and 560, and also an advanced technology vehicle is under development for further research activities. We have three ranges, the Thales range at Tumba and the Sriharikota range, which is operational right now. We also had a station at Balasore, which is now not operational. Large number of foreign rockets have been launched from lots of countries like the United States, the UK, the France, Russia. You see this M100, which was launched, more than 1,000 rockets have flown from the Soviet Union. And basically these are intended for research experiments of meteorological, scientific and technological developments, and also for international cooperation. This is the family of sounding rockets that we have. The RH-200, which is the smallest rocket we have, a low-cost rocket which can carry a 10 kg payload to a nominal altitude of 60 kilometers, which normally used for meteorology and also for technology demonstration. The next is the RH-300, a slightly larger rocket which can take 80 kg of payload to about 110 kilometers of altitude for D and E region atmospheric studies and also technology demonstration. The RH-560 is a two-stage rocket, heavy lift rocket, can carry 120 kg payload to about 500 plus kilometers of altitude, basically for the E and F region research and technology demonstration. And we have the advanced technology vehicle, which is a very powerful rocket and most heavy lift of our family, can take almost 400 kgs to a 260 kilometers altitude, basically used for microgravity experiments and technology development. We have two operational launch sites, as I indicated earlier. One is at TERLS in Trivandrum, the other at Sriharikota in Andhra Pradesh, which is on the east coast, and TERLS on the west coast. Both have got all these facilities like telemetry, tracking radars, real-time processing, real-time display, MET towers and balloon launch facility, ionosonde, radiosonde, all these facilities are available. In addition, for the larger rockets, we have the telecommand system also from Sriharikota. This is the RH-200 rocket, which we launched. Stage rocket capable of 10 kg payload, including a scientific payload of 5 kilograms to 60 kilometers, with a payload volume of 115 dia by 100 meter long, and also 100 mm long. Also, it caters to, it goes to a very high acceleration levels of 50 G, which can really qualify all those development electronics which are possible. And also used for meteorological studies. After its first launch in 1971, we have had 192 successfully launches of this rocket from. The RH-300 is a single-stage vehicle capable of taking 80 kg payload to about 110 kilometers altitude. It has a larger diameter than the 200, can take up to 280 diameter by 500 mm long. It can go up to accelerations of 20 G and mainly used for DND regions, and it can also take multiple payloads in a single flight. After its 1983 launch, it had almost 20 launches here. The RH-560 Mark III is a two-stage vehicle, can take 120 kg payload to about 500 km altitude. Again, the diameter being same as 280, but it can carry a longer length, about a meter long of payload it can take, and it can go up to 25 G. And mainly for E and F regions, it's a very good workhorse to qualify various launch vehicle systems. And after its first launch in 1973, it had about 21 launches so far. ATV is a new generation of sounding rocket, which have been developed for a specific purpose of flight demonstration of the air-breathing rocket. But it can, due to customer demand, we have adapted it to a microgravity experiment of 6 minutes. Taking a 400 kg payload, 260 kilometers altitude, can cater to a diameter of 420 to 560 mm diameter payloads also. The microgravity version, ATV EX we call it, is under development, and we expect it to be launched in a short time. Now, as I told earlier, we had 3,500 plus launches of our sounding rockets, mainly the RH-200, which have almost 1,400 plus launches, and also you see this 2,400 launches from TERLS, and that is what we have the numbers and the very successful launches so far. And many major campaigns we have had. The DIOS launch from SHAR, that is Dynamics of Indian Equatorial Atmosphere, in using 560 rockets, the Leonard Meteor Shower, the Middle Atmosphere MIDAS launches of RH-200, the Surya Grahan campaign. To note, we had 11 launches in 2 days. In 2010 January, we had, I'll come to the detail of that. And the last was the SAUR experiment, which was initiated by SPL. We had 2 launches in 18 and 21 using 300 and 560 launches. This is the DIOS, a small version of the a clip of the DIOS. It is in collaboration with the German Space Agency. We had 3 560 launches from Sriharikota, including the DLR and university payloads that achieved all the objectives of the requirement of the scientists. The Surya Grahan campaign on January 15, we had an annular solar eclipse, and we had 11 rocket flights over 2 days. That is the day of the eclipse and the next day control launches, near simultaneous launches from Sriharikota and from Trivandrum, carrying a plethora of scientific equipment. Okay. These are some of the payload assemblies which you can say, including the trimethyl aluminum payload, the NV and LP payloads. All these were flown in Surya Grahan campaign. The advanced technology vehicle, as I told earlier, is a 2-stage vehicle which has been developed as a flying testbed for demonstrating the air-breathing propulsion scramjet system. We had 2 flights. It is a new development. It's an unsymmetrical body, that is, you see here the 2 air-breathing engines on either side, and hence the fins had also to be made unsymmetrical. With that, we had first flight in 2010, which is characterizing the unsymmetrical vehicle, and the second flight in 2016, which successfully demonstrated the scramjet engine with twin engines with a total flight duration of 300 seconds, achieving supersonic combustion with auto ignition, flame holding, and sustained combustion, and also positive change in vehicle acceleration was also measured. And okay, one more aspect to be noted in this, you see here this carpet is a specific Mach number dynamic pressure window in which the scramjet has to be tested. We could achieve that, and in the first flight itself we could achieve that, and that is how the scramjet engines were successfully demonstrated. The scientific payloads which we have flown include the electron density and neutral wind probe, the Earth atmosphere composition probe, the Langmuir probe, the electric field probe, and the chemical payload of trimethyl aluminum, which have also been flown in these flights. Now, the last campaign, the SAUREX campaign, we had 2 flights in that. The RH300 Mark II with the TMA flight, in which we had also the NV and the LP also sitting there. We had it from TERLS in 2018 April. They predicted against a predicted apogee of 99 kilometers. It has gone to 108 kilometers, expelling the TMA fluid from about 90 kilometers of altitude. We estimated 90 kilometers, but we got it from 90.3 kilometers, and initiated about 100 seconds for a flow rate of 50 grams per second for 43 seconds. Exactly as per predicted, we got the flow rate. And okay, this is the test. Now, in the Suryakiran flight, this TMA emission expulsion was not successfully demonstrated. So to demonstrate the successful expulsion in vacuum, we had to do a high altitude test at Sriharikota facility, and it gave us confidence to go for the flight. And with that confidence, we had a successful flight in which the chemiluminescent trail of the TMA was photographed from 4 locations, distinct locations: Trivandrum, Kanyakumari, Tirunelveli, and Kollam. And with that, they used the triangulation method to estimate the propagation of the trail. And with that, we had a very successful mission. The second flight of under the SAUREX program was the RH560 Mark III flight, in which again we carried the similar experiments, but with the NV and LP in 2 different modes, and the TMA, the larger canister with a larger expulsion rate, we could fly. This shows the integrated payload of the flight. And in this also, we use the Monte Carlo simulations to achieve the injection timing sequencing against a fleet prediction of 470 kilometers. The vehicle had achieved 512 kilometers, thereby achieving the peak altitude and all the desired objectives. This is the TMA payload under the on the launch pad checks which are going on, and here you see the expulsion characteristic of the TMA. As per prediction, it has been obtained from 96 kilometers to about 59 seconds. It expelled at a rate of 255 grams per second. That here also at 4 different locations: Chennai, Gadangi, Kalpangam, and Kavali. The trail was photographed and used for further studies. The next is our aerodynamic decelerator, which we are envisaging as a precursor for the stage and payload recovery. This will also want to indicate that the microgravity experience which we are proposing in the ATV series can also be maybe recovered through these methods. This experiment with you see this toroidal aerodynamic decelerator, which will be kept folded inside the nose cone, will be deployed at the desired altitude of about 70 plus kilometers, and it will be brought down within a very shallow aspect and will be recovered using this IAD. Now, the sounding rockets we can give you as offer you as an ideal platform for your space science experiments. This basically will cater to the altitudes which are inaccessible by balloons and satellites. That is, our balloons go up to around 40-45 kilometers. This will cover from that to the near altitude of the satellites, about 400 to 500 kilometers, and as a flying testbed for technologies for space systems. It's a very low-cost tool for your scientific experiments and payload capability up to 400 kilometers. We have very short turnaround time. They're simple and versatile. And these are suitable for experiments DE and F regions of the atmosphere. We have very qualified and reliable telemetry and tracking system, payload deployment mechanisms like nose cone ejection, boom deployment, door ejection, chemical release. All these things are proven and available. We have real-time data processing and data uplink. We can give you vehicle attitude measurements and also with near simultaneous launching from TERS and SHAR. And also we have multiple scientific experiments in a single flight as shown by our SAUREX and DEOS flights. And the research avenues are plenty, from aerosol, plasma solar physics, auroral and non-auroral phenomena, air glow, solar flare emissions, plasma bubble, radio propagation, microgravity experiments, and chemical release systems. And we have the Sounding Rockets project at VSSC. We call it the ATVP. We will develop, realize, and launch sounding rockets for scientific purposes, technology demonstration using the sounding rocket as a platform, and we cater to the mission and aerodynamics, configuration control and quality assurance, structures of the vehicles, rocket systems, avionics, integration and launch, flight data analysis and management. With this, I thank you for your patient hearing and also enthuse you to bring your science experiments to us for launching using sounding rockets. Thank you.
Sir, thank you very much for your detailed presentation on sounding rockets. Here, as the time is there, on small question, like in a PS4 platform, do we have any qualification tests to be carried out for the proposed sensors or payloads?
We do have qualification procedures, which involves the environmental tests and also the ground qualification of these packages and also sensors. We have a very strict and detailed procedure for that, which we can always share with you when your systems are ready or getting ready.
Yeah, thank you, sir. Any questions from the audience? Can be you can post in the chat box. So thank you very much, sir, for your detailed presentation.
Okay, thank you very much.
We will move to the next presentation. Next one is ISRO sound rockets, overview of instrumentation system for space science experiments. Virendra Keteva from VSSC. Sir, kindly load your presentation.
Is it audible to all?
Yeah, you are audible and your PPT is visible also. Sir, you can start your presentation.
Yes. Good afternoon to all. I am Virendra Kateva, working in Advanced Technology Vehicles and Sounding Rocket project. And just before that, our project director has given a brief overview about the ISRO sounding rocket, and bunch details were available about the vehicle and the kinds of systems we are having. And in this presentation, we'll discuss, we'll have an overview about the instrumentation system which we are going to provide our space scientists for their different space experiments. And, it was already talked, and as we know about it all started with the Nike Apache experiment, and it was the first sounding rocket mission which was done through done at Thumba on November 1963. And the payload which was used here is the sodium vapor trail experiment, and we have successfully done it, and it was a US based payload, and all photographs, everything was visualized here, and it led a next generation experiment, and it created a roadmap for ISRO to work in this space domain experiments and give the next level facilities to our scientists, as well as facilities to the different domains of satellite technologies. as already discussed, we have a plenty of missions right from early 60s, and with different test formulations, we developed our sounding rockets. We have a large number of sounding rockets vehicles, and they are characterized based on their capabilities with respect to their payload, and put their payload into the right altitudes to carry out the predefined scientific experiment. If we talk of the sounding rocket structure, the critical part we can see here highlighted as a payload area, which includes all the scientific instrument as well as avionic modules. And in this presentation, we'll mainly focus about the payload domain, and we'll discuss kind of vehicle avionics, instrumentation, and some of the payloads which were already flown to carry out certain scientific experiments. So let's see the operational sounding rockets which are available with the ISRO. These are the present operational sounding rockets which we are flying based on the demands from the scientists, and will provide all kind of footprints right from the 1U to 4U with respect to different class of vehicle. Let's see some of the major scientific payloads which we have flown in our sounding rocket in last 3 to 4 decades. You can see the NVA and LP probes, popularly known as Langmuir probes, and used for different used for measurement of electric fields are different through the rhythms of the atmospheric layers. And TMA, popularly known as trimethyl aluminum, which is already discussed with you, and EAC and some copper chaff experiments. We are having regular copper chaff experiments from our Thumba station, with the help of which we can characterize the wind velocity from the altitude of some 60 kilometers to the down at some 20 kilometers. This is a typical pictorial view. We can see in the left side how scientific payloads can be integrated. And you can see in the left side all LP and NB probes in the recent mission what we have carried out through with the help of our SPL team and VSSC, and with suitable processed electronics and all. We are assembling it into the payload, and this payload will be kept as the stacked module over the motor case, and subsequently will carry out all our mission, which are pre-decided based on the kind of sequencing, kind of measurement schemes and data acquisition units, and will provide all such facilities to our space scientists. Let's see what we have developed so far to carry out our space missions. We'll discuss about the major parts to monitor the vehicle health, not only for the monitoring purpose of the vehicle health, even same sensors can be used for health status of scientific instruments which our scientists want to fly as a test bed in our sounding rockets. First one, we can see accelerometers, and we are having a large variety of accelerometers which we will discuss further in the coming slides. Apart from that, shock and impact sensors, vibration sensors, we have different variety of navigational sensors based on the positional and right attitude information about the sounding rockets throughout its trajectory. And we have also the structural and structural analysis or structural monitoring of the sounding rocket through our FOSS system. And different varieties of pressure transducers are also available with the ISRO to see the effects of our motor. Even through different layers, we can have the pressure measurement, and very accurate and very fine tuned sensors are also available with VSSC. Let us see some of the sensors. Left side, you can see accelerometers. We have a wide variety of accelerometers, as I already discussed. Even right from 30G to 100G, we can measure successfully in the flights, and we have a very good heritage and proven sensors. And in last so many years, and we are developing our sensors to the much advanced level by reducing their non-linearity aspect, as well as giving better and better resolution to our scientists or research people. Apart from this, if we talk about vibration sensors, as we already know, our sounding rockets experience, or any kind of launch vehicle they all will experience such levels of vibration, as well as there will be a subsequent pressure build-up in the motor chamber. So in order to have characterize their profile, and as well as if you want to see how it is working in the right environment, we all have miniaturized as well as high quality with respect to the better resolution and very good linearity aspect sensors. All such details are available in our websites also. These are the recently developed shock sensors, rate sensors. Rate sensors can typically considered as our navigational sensors. Apart from this, recently developed our fiber optic sensor system. It's a collaborative combined system which is having the health monitoring with respect to strain as well as temperature measurement. So throughout the different altitudinal variation of atmosphere, we can have the measurement of temperature, pressure, and all such profiles also. These are typical avionics support which we can give to our especially to our space scientists for their particular research. Like we can have the acoustic and pressure sensors, so they can measure their acoustic levels as well. They can measure the pressure throughout the different layers of atmosphere with the very accurate numbers. Suppose since we know if we are going towards the vacuum, the pressure levels are decreasing in the vacuum level even less than 10 to the power minus 6 bar. That low level we are getting it. So we are having a fine accuracy of sensors, and we can fine tune even with the offsets, and such all capabilities are available with the ISRO. Apart from this, magnetometers are also available, which we can have the magnetic fields of, around the Earth or any kind of other orbital missions. It can be used, and it has the capability to have measurements around 60,000 nanoteslas of magnetic fields. We can easily measure it, and a wide variety of navigation systems are available with the ISRO. Recently, we have developed NAVIC-based navigation sensors also. And they are in the combinational form, means they are coming along with our accelerometers, and you can consider as with the combination of NAVIC as well as other GPS satellites. We are using as a combinational system, and which helps providing the accurate information about the attitudes, and it is very useful with respect to the launch vehicle as well as the certain sounding rocket experiments. The most critical parts are the data acquisition system. The kind of data acquisition system ISRO is having is much varying. It is always customized with respect to the designers, or you can consider the principal investigators concern, and we can customize and can provide the data rates as per their requirement. The kind of resolution, all such facilities are available with the our newly designed systems. And video imaging system. Recently, we have developed our new kind of video imaging system, which can have a high quality resolution, even 1080 pixels of video quality in the right real-time domain analysis. It is possible to be down telemetered at 2 Mbps data rate at ground. So, and another critical part is sequencing and power system. We are having a very reliable power system in forms of lithium-ion batteries, in forms of supercapacitors and hybrid capacitors with different capacities, 1 Ah, 0.5 Ah, even 5 Ah, 50 Ah. This all depends upon the user requirement, and we can support well for their avionics. And even sequencing is a very critical part, since sometimes the requirement for sounding rockets is purely on the time-based sequencing, and we are having a very precise and accurate sequencing commands with our processor systems. Even with an accuracy of 20 millisecond also, we can have a suitable commands at the predefined timings. Not only predefined, we can have real-time basis. You can consider a sequencing system through our uplink capabilities. apart from this telemetry and tracking, and if we talk about telemetry and tracking, we are having a wide variety of telemetry ranges available. Typically, ISRO is working in S-band telemetry, and we are having 5 bands of availability in VSSC as a ground station, as well as other station available at Harikota SDSC Shah. We see these are some of the features of the acoustic system, acoustic sensors as well as thermal sensors, which are recently developed by our VSSC team and other ISRO centers. And right, you can see the measurement range, even 100 dB to 100 to 180 dB. You can say the OSPL level we can easily measure in the real-time environment. And the frequency response also all are customizable. They are having programmable electronics available with the sensor. So and the temperature, basically in the dynamic environment which is available, you can consider from the 10 kilometer of range to the upper altitudes of some 400 kilometers. So we can cope up with such an wide varying temperature ranges and pressure levels, and you can consider the kind of flux and everything which is available throughout the trajectory. We can isolate easily with our advanced or well-developed mechanical and robust structures. Talk about the thermal sensor. Recently, we have developed a lot of a wide variety of thermal sensors with having very good accuracies. Even you can see less than 3% of full-scale output accuracy we are able to develop with our sensors, and this all depends upon the kind of requirement by the designers, and we can provide support for their system.
2 more minutes per recommendation.
Yeah. This all we have discussed previously. Magnetometers, you can see we have improved our resolution also. 16-bit resolution we can give with respect to our 60,000 nanoteslas of measurement range. These are recently developed navigational system being developed by our counterpart IISU, ISRO. And you can see, as I already talked about this combined, or you can say hybrid system we are developing. It's a combined unit of magnetometers as well as feature of GPS, even Gagan as well as Navig. So we can have an accurate altitude information about the launch vehicles, or you can say sounding rockets. This is being recently developed data acquisition systems, and it's a hybrid kind of nature being developed by VSSC. And we are having, as you can see in the, it's a software defined radio based transmitters, and people have started using in the launch vehicle some couple of years ago, and we have come across sounding rockets facility also. The main advantage is the kind of bitrate you can see in the right side we can provide is around 8 Mbps. So even raw data which are available throughout the flight need not to be processed and directly can be transferred to the ground with such a high data rate capabilities. And you see the power and all, it is all upgradable, and you can have a better link margins. You can see it's a fully digital transmitter having a latest modulation techniques which will improve the link margin to further levels. So with this miniaturized and you can say miniaturized and low power consumption modules, it will provide better and better, bigger and bigger footprint for our scientific payload, and it will provide a very highly accurate you can say transmission system along with the better resolution terms, because we are using here all 12-bit ADCs, so resolution is improved in terms of 12 bits. From this, as you talked, video imaging system, we are capable to have live video telemetry. Even Blu-ray quality videos can also be processed and down telemetered in the real time to the ground. So such capabilities we have developed, and it is highly robust in nature. So that since we already have one confidence, if any of the avionic packages being flown in the sounding rockets, it definitely work in the other launch vehicles. So collectively we are using a mill grade as well as a court-based system also, based on the kind of requirement where the avionic packages to be placed. Accordingly, we'll use the component and suitably qualify through our predefined environmental levels, and other in-house you can consider the ground level test. After all such qualification, we'll fly our avionics system in the sounding rockets. And this is critically, you can consider the sequencer system. The latest being developed sequencer systems comes as a hybrid nature along with the relay card, the kind of you can say commands we can provide along with the different kinds of transducer channels, instrumentation amplifier, and the processed data in a very accurate forms, and by suitably removing the noise available in the measurements. All such facilities are available in the acquisition parts of our sequencer system as well as data acquisition system. Such packages are being developed in-house, and we are flying in our sounding rockets. These are the two launch station. I think we have already aware of the such details about this tracking system. The only thing I want to highlight is we are capable of uplink and downlink at the same time with different links, both at VSSC as well as SDSC SHAR. At last, we'll conclude with the offerings what sounding rocket can give. So we are already discussed. We are having a highly qualified, reliable sounding rockets, and we can explore easily up to DE and F regions of atmosphere. And we have a very reliable avionics system, a miniaturized low cost, which can provide the telemetry as well as tracking of the sounding rockets, highly reliable power systems, which are readily available with the VSSC and can provide support to the space scientists for their instrumentation schemes as well as their scientific payloads. We can provide a better integration support both in terms of mechanical as well as electrical integrity, and we have quite good experience in handling the telemetry, payload checkout, and data processing system in different domains. Apart from this, we have the highly you can say the newly designed systems which are having very high and accurate resolution. All such data are always required by the researchers for their space experiment, so they need not to compromise with the data rates. Since we already informed 8 Mbps of data rate in the real-time domain, we can provide. Apart from this, we have the capability to provide multiple downlink and uplink at the same time with the varying data rate capabilities with the same or you can say the similar sounding rocket mission. And most important, you can say vehicle as well as scientific instrument health monitoring is also available, and scientists can have monitoring or proper real-time display monitorings of their instruments throughout the flying regime, and after that they can have a PFA post-flight analysis they can do easily. And apart from this sequencing commands and all, typically of the order of 20 milliseconds we can have sequencing details. So apart from this, we can provide support to the scientists and other agencies to qualify their scientific instrument as well as payloads for various environmental level tests like vibration test as well as spin test. You can consider as the acceleration test. All such facilities we can provide as a collective efforts. So that's all from our side. And
there is one question from the chat box. This is from Ramesh. So is there any website or web address to access the open data from sounding rockets, especially neutral winds and temperature? That is the question.
Yes, actually VSSC, under the tab VSSC, we are having ATVP project. Their all sounding rocket details are available. And apart from this, typically the temperature levels and all, if somebody sensor details somebody wants.
Not sensor details, so this neutral wind information and like zonal velocity and meridional velocity, that information and temperature information really are you providing in open platform? That's the question actually.
Yes, for such it's not an open source, and all such information are available with our SPL team. They can contact with our SPL for this payload details.
Yeah, I think it answers Ramesh sir your question. So we thank you very much, and we'll move to the next presentation. And for today's first session, the next presentation is scientific payload electronics for electronic and ion density measurements on board ISRO sounding rocket by Srilata P. STL-ESSC. Ma'am, you can load your presentation and you can start. 20 minutes is allotted.
Good afternoon to all. Is my presentation visible?
Yeah, yes, ma'am.
A very good afternoon to all. So all we have been hearing about the sounding rocket of ISRO. So I'll just touch upon how we have developed some of the scientific payloads and the payload electronics, basically for the measurement of electron and ion density measurements, and use the ISRO sounding rocket for the measuring purpose. So I'll be just touching upon an introduction with scientific objectives and working principles, some of the guidelines for the scientific payload design for the sounding rockets, and NVLP is the main payload that I'm concentrating on. So some of the steps of designing the payload and the electronics and the tests, and a glimpse of the payload performance with, during the SAUREX mission. So as an introduction, sounding rockets, we have already heard enough, like sounding rockets are the research rockets for probing the upper atmospheric regions and for the space research, and they offer a very low cost platform to test all new designs. And we are using the RS-300 and RS-560 series for upper atmospheric studies, and the 300 can go up to 120 kilometers and 560 up to 500 kilometers. The 300 will be launched from Trivandrum TERS range and the 560 from the Sriharikota range. So the first step in designing a scientific payload is the scientific objective. So scientific objective is broadly defined as the investigation of atmospheric processes over the low and equatorial latitudes. And with respect to that, we have developed two scientific payloads, which were called the NV and the LP, and which were flown successfully as part of the sounding rocket experiment in RS-300 Mark II and RS-560 Mark III. The NV probe is the electron density and the neutral wind probe, which enables simultaneous measurement of electron densities, and neutral winds in the ionosphere. The basic probe is a horizontal structure with two identical arms and having a field-free drift tube with two grids, and which are maintained at a constant potential of -1 volt, which will help to attract ions. Coming to the Langmuir probe enables measurement of ionospheric electron density and irregularity strength, and it is basically a gold-plated metallic sphere which is kept at a fixed voltage of +4 volt, and it attracts the ambient electrons. So with these two probes, we have a single electronics module, which we call the NVLP electronics, and this is used for providing the biases to the probe, as well as to receive the current generated from the probe due to the incoming ambient charges. So let's see how all this together work. So this is a simple block diagram to explain the total working of the system. The grids of the NV are given a negative bias to attract the ambient ions, and they constitute a current which is collected by the Faraday cup, and it is proportional to the neutral wind in that region. This current is received in the NVLP electronics. The LP is given a positive bias which attracts electrons constituting a current proportional to the electron density in that regime. Both of these are collected by the NVLP electronics, where the current from the probe is converted to voltage and sent to the rocket telemetry. So how do we go about designing a payload for the sounding rocket? There are some general guidelines which need to be followed. The size of the probes and package should be within the nose cone dimensions, obviously. And the sensor and the electronics should have a very fast response, as they are sampling the atmosphere while moving at a very fast rate. And the weight of the package is to be within the payload capacity. The power for the package is from the battery of the sounding rocket, and so power consumption of the package should be within its limits. Commercial components are allowed, unlike satellite missions, but the main thing is that the electronic package with these commercial components are also to be qualified using special environmental level tests, which we call as the gate test. So coming to the NVLP specifically, the payload design, as I have already mentioned, it starts with the scientific objectives from which the parameters to be measured and their expected range of values are identified. The measurement parameters basically define the sensor design, the parameter range, and the sensor output, format define the front-end design of the payload electronics, and the rocket telemetry standards define the output interface from the electronics package. So we have gone for analog type of data, and the analog data has to be within the range of 0 to 2.5 volt. And the sensor output form is basically a current. So we take the current as the input of the front-end design. So deriving from that, we'll just touch upon the specifications. We are, as already mentioned earlier by PD of the ATVP, he was mentioning we had 2 sets of payloads in RH560 and a single pair of payload in RS300. That is, in the RS300, we had one NV and an LP, and in RH560, we had NV operating in 2 modes and a spherical LP and a cylindrical NP. This NV and the first 300 NV or ion mode is common in 300 and 560, and the LP sphere is the commonality between RS300 and 560 for both the payloads. So the current range that needs to be measured was first calculated with respect to the scientific requirement and the sensor details. So the current range, as you can see, the NV, the range of NV is from picoamperes to nanoamperes in all the cases, whereas for the LP LAMIO probe, it is from nanoampere to microampere, which implies that all the front ends are not exactly identical, though we need some changes. So with the current range that, with the details of the current range got, the electronics design starts, the FE design starts by defining the current range for the electronics, which should be encompassing the required current range. So everywhere that was taken care, and this is the current range used for the circuit design and for laboratory tests of all the electronics package. So front-end design starts there, and now we have some interfaces which also play their role in designing the total electronics. The first is the power interface, which is the battery. The battery power requirement is given, and the regulated power will be got from the sounding rocket. And the next is the probe electronics interface, which has 2 sets, like the bias potentials, which need to be given from the electronics to the probes, and the data signal lines, which carry the signals or the data from the probe to the electronics. The third is the main rocket telemetry interface, which is the, specific for that rocket telemetry. And here we have the output voltage range defined as 0 to 2.5 volt for all the channels. And we have a number of analog data channels, that is 19 were there for RS300 and 25 were there for RS560. Out of this 19, 15 were for the data channels that will be catering to the NV and the LP data, and 4 for the housekeeping or HK parameters, which is the health of the payload. And similarly for the RS560, we had 19 data channels and 6 for the HK. So what are the general requirements? Once we know what is the specification that is needed for the electronics, we'll go into the general requirements that we have already seen that this is the requirement is to measure very low input current. So that is our first and prime requirement. And the design is to be very simple and easily repeatable because we have multiple launches. And for this, a careful selection of the components has been done to cater to these scientific requirements. And all these are to be housed in a single, or the electronics is to be housed in a single mechanical chassis. The size of the chassis is already predefined. The cabling from the probe, which carries the low current, should be of low loss type, and preferably they are used. The one that we used was shielded cables. Proper signal conditioning at the output end is to be ensured for seamless interface with the rocket telemetry. So now let me take you through some of the design steps for the NV LP electronics. We have used a very sensitive I2B with a very fast response as the front end. And as the required current range is more than 3 orders, suitable amplification channels are also provided. The biases to the probes should have to be very highly stable, as this is a major factor defining the measured current. The output is signal conditioned for limiting to the telemetry voltage limit and filtered with respect to the sampling rate in telemetry. This is one of the package. This is our NVLP package that was realized for the RS300 sounding rocket. Once the payload is electronics is realized, we take it through a host of laboratory level tests, which the block diagram shows a broad overview. Like we have the electronics, and there is a low current source which will simulate the output of a expected from an NV or LP probe. So the low current source will we use a low current source for testing each of the channels, and the output is taken as a 0 to 2.5 volt range, which will be taken to a multi-channel data acquisition card and an in-house developed LabVIEW-based software, which will form a checkout, and it gives a response of whatever is given through the current. Thus, we can totally characterize the electronics used in the laboratory level test. So these are some of the pictures. And for RS560 Mark III, as already told, we had two sets of probes. The two sets of probes as going for a stacked level of electronics, almost similar. So, but during the test, it is like double the effort. We have to test all these channels for the varied current ranges, and the data is already saved in that checkout PC. The laboratory test involves the functional tests, which, as I have told, that all the input channels are wherein all the input channels are tested individually using the low current generator, which will form the source. The source is varied within the specified range for each input, and the response is acquired using the checkout system. So this involves basically three types of tests. The first is for the characterization of the electronics, wherein fixed input currents are given, and the output values are measured and tallied to find if there is any offset. And the speed of response of the total system, wherein the current is varied in a very fast manner in ascending and descending modes, encompassing the total range required. And a stability test to see whether there is any offset that is creeping in within the total, within a duration of 30 minutes. This is also done for 3-4 ranges. Following the functional test, we have to take it through a set of environmental tests, which is called the gate test. This ensures the reliability of the packages that is to be flown in the sounding rocket. The gate tests have to be qualified, or the package has to qualify the gate test before getting it integrated to the final rocket. The gate test involved a series of set tests, which is called the initial SRC, or the standard room condition test, and a 96-hour active burn-in. That means the package will be switched on for 96 hours continuously, and the data will be recorded, and any change in the performance will be noted. If there is any change, that actions will be taken up. And following that active burn-in, there is a thermal test wherein the package will be kept at a hot, package will be performed in a higher temperature, and similarly for a lower temperature. Then the package will be kept in a vacuum, and there also it will be tested. Following that, it is a vibration, acceleration, and after all these tests are over, there is a final standard room condition test, wherein that will actually qualify whether the package can be flown on the rocket. After all these gate tests are over, before integration, we have an end-to-end compatibility checks with the probes in vacuum, electronics outside, and the rocket checkout. This will totally ensure that the total package can go in as part of the sounding rocket. So this picture is the integrated one for RS300 Mark II, wherein this is our Langmuir probe, this is the NV probe, and this is the NV LP payload electronics. And the recent one with RS560 with 2 pairs of probes, it was a indigenously, or like it was very nicely kept within the nose cone dimension of one NVLP. There was some lot of mechanical integration that was going on, which is to be mechanical integration which was changed for accommodating these 2 payloads together. That is, and we have the 2 Langmuir probes here, and this is the 2 pairs of NV probe. And below one is the stacked electronics box. So let me conclude by just showing 2 sample plots of the payload performance, which was done during the SAUREX mission. The measured currents in both 300 and 560 for one mode of operation of NV and LP are like catering to the pico to nanoampere range, and the LP from the nano to microampere range and very much within what is designed within the designed limit. So this is a sample plot of the LP, wherein this is for a shorter duration 300, and this is for the longer duration of 560. With this, let me conclude. Thank you. Let me thank the organizers also for giving me an opportunity to present this paper. Thank you.
Yeah. Thank you very much, madam, for your detailed presentation on the NV4. Any questions on this presentation, you can type in the text box. Yeah. So if not, then Rana sir, coach, sir, we came to the conclusion of this first session on day 1. And here we had one lecture by Dr. K. Rajiv sir, then followed by 4 flash presentations, and subsequently we had 3 presentations, oral presentations we had. And very nicely we got the opportunities, various opportunities that on the PS4 orbital platform we came to know, with detailed information given by Dr. K. Rajiv sir. Then later on, we came to know the information about the sounding rockets, the type of opportunities that are being opened up for the new developmental new developments and the sensors. So with this very nice session we had, and we came to the end of this session for the first session. And Rana sir, if you have some points you can add, otherwise we'll close it.
No, I think it has been nicely summarized by you, so I don't have any further points. I think we can close it. Thank you.
Yeah. So the request to the LOC team. So the presentations are completed, sir, and let us break for a tea, and then we can add to the next session by 16:30 hours.
Thank you, sir. We'll break for now.
Thank you, host.